Okay, so for the last part, it's about the variance of the parameter. This is the equation. It is a bit different than the equation in the last chapter for the simple linear regression. So this is the formula. Variance of the parameter bj, so it could be b1, b2, b3, and so forth, is equal to this term, which is the variance of the error terms, divided by SSTJ, so it is the total sum of square of that x variable. So if it is SSTJ, if j is equal to 1, then this total sum of square is about the dispersion of x1 around the mean of x1. And if it is SST2, then it would mean variance of the x2 value around the sample mean of x2. Okay? And then times 1 minus r square. R square comes from the auxiliary regression. Okay? So it means I regress xi on all other explanatory variables. So this r squared derived from the auxiliary regression gives you an indication of the extent of relationship between xi on the other x's. Then it relates to imperfect collinearity or imperfect multicollinearity. Okay. Now I want to know the impact. Okay, what are the factors influencing the variance of the parameter? Again, just to remind you, we want the variance of the parameter to be as small as possible. First one, bad news, if this numerator term becomes bigger, meaning if the variance of the error terms, which implies the noise, okay, if the variance of error terms increases, then sorry, the variance of the parameter would also increase. And the reason we already explained in the last chapter, because the more variation or the more noise there is in the unobservables, which means most likely omitted variable bias affecting y, making it more difficult to precisely estimate the sample regression parameter, thereby causing variance of the parameter to become larger. Second one, it's about this total sum of square of x. If there is more variation in the x, then the denominator gets, this term becomes bigger, then the denominator gets smaller, then the variance of the parameter becomes smaller. Like the reason we already explained in the last chapter, because the more spread out is the sample of the x1 or x2, okay, the easier it is to trace out the relationship between the x's and the expected y value. And then the easier it is to estimate the sample regression parameter. Okay. The third one, this is the R square from the auxiliary regression. The greater the R square of the auxiliary regression, meaning the strong relationship or strong imperfect collinearity or imperfect multicollinearity between the explanatory variables, then sorry, the variance of parameter would increases. Okay, so mathematically, if the greater this term 1 minus R, if the greater is R square, then 1 minus r squared will become smaller. Then the smaller the denominator is, then the greater the variance of the parameter. Okay, in other words, I'm facing a dilemma actually. Remember, the main reason why I want to add more explanatory variables is that we want to avoid noise in the error term, or we want to avoid committing underfitting. So by taking the omitted explanatory variables out of the error term, remember that IQ, years of work experience example, by putting them explicitly as explanatory variables and running the regression as multiple linear regression model, then it increases our chance to be able to meet this assumption, which is the mean of the error terms is equal to 0 at each x. Okay, then it helps reduce the variance of the error terms. But at the same time, if I run the multiple linear regression model, it leads to greater likelihood of committing imperfect collinearity or imperfect multicollinearity, then causing this R square to become higher. And then at the end, somehow it caused the variance of the parameter to go up. So we are facing a dilemma actually. Okay, and then remember, if the variance of the parameter or the standard error of the parameter, remember standard error of the parameter is the square root of the variance of parameter. So if the variance of the parameter and then subsequently the standard error of the parameters are biased and unreliable, then it would lead to all sorts of problems with the reliability of your confidence interval hypothesis testing results. Okay, and then I have a mathematical example here to show that the more serious the imperfect collinearity or imperfect multicollinearity is, the more serious the impact on the variance of the parameter. So again, I have to use this equation. To simplify things, I would assume this term, the variance of the error terms, divided by SSTJ is equal to 100. And now I want to have 4 cases on the R square from the auxiliary regression. Case number 1, no relationship at all between x1 and x2, but in real life it is quite difficult to find. So for example, I run the multivariate regression. Quantity demand of BMW is a function of x1 price of the milk, x2 price of BMW. Okay, and then I run the auxiliary regression, x1 regress on x2. I think price of the milk and price of BMW wouldn't have any relationship at all, but I actually commit overfitting by including x1 in the regression because price of the milk should have no impact on quantity demand of BMW. But going back to the R square of the auxiliary regression, 0, then I substitute 0 here. Then at the end, luckily, no impact on the variance of the parameter. It remains unchanged as 100. Good news, but it is rare to find, as I said, find an example in real life that x1 and x2 are totally uncorrelated. x2, there is a little bit a weak imperfect collinearity between x1 and x2. So this is an example. Marks explained by study hours and then the father's years of educational attainment. Maybe a little bit of relationship, but not that strong. Okay. I think I mentioned in the past that we could have some students that the father never went to school, but somehow the kids work very hard. But in general, a little bit of relationship, positive relationship. So 0.2 is the R square of the auxiliary regression. Then I substitute 0.2 here. So do you notice that by running it as a multivariate regression? And this case, luckily, x1 and x2 are only weakly correlated, but it still caused the variance of the error of the parameter to go up. Do you see the increase from 100 to 125? Okay. Third case, now the imperfect collinearity between x1 and x2 gets stronger. So this is an example. Marks explained by lecture attendance and tutorial attendance, very strong relationship because those who attend lectures are also the one who attend tutorials. So 0.9 is the R square of the auxiliary regression, and then you substitute 0.9 in the equation. Do you see the huge increase in the variance of the parameter? It goes up to 1000 now. Okay. And then the last case, perfect or exact collinearity between x1 and x2. Remember this example? Noise level explained by number of people and number of eyes. But remember, one person has 2 eyes, 2 persons have got 4 eyes in total. So x2 is actually exactly the same as 2 times x1. So if I run this auxiliary regression, x1 regress on x2, the R square is exactly equal to 1. And then I substitute 1 here. Then I have 1 minus 1, which is 0 in the denominator. So actually, this is so bad that the variance of the parameter is unspecified. The reason is that due to perfect collinearity, exact linear relationship between x1 and x2, sorry, it is not even possible to derive regression parameters. Okay. The collinearity is perfect or exact, that it ruins the regression completely. So it is not possible to run the regression and impossible to derive the variance of the parameter. So this is the worst ever case. Okay, but at least from the 4 cases, you know that the relationship, okay, if I run it as multiple linear regression model and as the extent of relationship or linear relationship between the explanatory variables gets stronger, then we suffer stronger imperfect collinearity. Okay, and then it would cause an upward bias in the variance of the parameter, which is bad because if there is bias, especially upward bias in the variance of the parameter or subsequently the standard error of the parameter, then it would lead to the results of confidence intervals and hypothesis testings being unreliable. Speaking about confidence intervals and hypothesis testing, so chapter 4 is devoted completely to conducting these tests, F-test, T-test, confidence intervals, hypothesis testing. Okay, so see you later in chapter 4.